Let's talk about dual system. So the system we were talking about previously was just a framed system of reinforced concrete. But what do we mean by dual system? Any ideas? Shear walls plus frame. So generally that's what majority of the buildings are made of, especially high rises, is there's a shear wall system, which is your main lateral force resisting system. And then there's your gravity system, which is the frames. And they interact in very different ways, depending on the material. If it's a reinforced concrete structure, the interaction is different. If it's a timber structure, the interaction is different. If it's a steel structure, the interaction is different. So a typical dual frame system, you have shear walls in both direction. The length of the shear wall is calculated using your shear demands, essentially base shear, and then you divide that over the length of the wall. It has frame elements as well as for reinforced concrete, it's generally a monolithically casted shear wall system on both directions, long direction and short direction. And the frame is very rigid with a rigid diaphragms. It's not an assumption, the diaphragm is rigid and the beams bend in shear mode. Do you know what the diaphragm is? Can you be louder? You know what a diaphragm is? What is it?
Act as a rigid body to transfer slab loads to beam and column.
Slab loads to beam and column. With, what's the specific mode of deflection or mode of action? It's like a deep beam bending, right? So essentially it's a rigid diaphragm that transfers loads into shear walls. Just because of the duality of the system, by duality, you mean you have a very rigid shear wall system, which is very stiff. And the frame is also stiff, but not as stiff as shear wall. You have different curvatures that you have to deal with when a building is deflecting, right? There is the curvature of the wall and, the curvature of the frame and the curvature of the wall. Generally, because of the disparity or the difference in stiffness, the curvatures are in different directions. So if it's convex outside, then the convexity is inside for the walls. So it's bending like this, but this would bend like this. And when they interact together is a shape profile like this originates. Essentially, what it says is the main takeaway from this figure is the summation of these two shapes gives rise to what we call an inflection point. The inflection point is something where the bending moment is zero. And in a building, how do you calculate that inflection point? The shear force is maximum, but also the bending moment is zero. So you can play around with these two, you set up those equations and you can play around with these two. Clear so far? Although we will not design something like that, a newer concept is something called a spine system. Do you know what a spine system is? You know what a spine is? Like your spinal cord, essentially a stiff bone which gives the structure rigidity. So this can also be considered as a spine if you design it that way. However, if it's a spine, the interaction is not like the one I showed. It's a much more independent interaction. So a lot of newer, taller structures with performance-based design, what they are doing is they are taking this out and putting it right next to the building and not within the frame of the building. That way, you have a very rigid spine. It could be a pivoting spine, it could be had some other kind of motions that it's interacting with the frame, but that's what's taking all the lateral forces in the system. So just to give you a glimpse of the future, we are not going to design that, but that's what really being pushed at in different University of California, Berkeley is doing a lot of research, Stanford is doing a lot of research on that. There are some structures that are using steel E-link connections. They employ a spine system. The steel E-links, when coming together for tall buildings, are essentially considered a spine and designed in that way. So when you have to design this using performance-based design, right, with direct displacement-based design method, now your multi-degree freedom system looks something like this. Your SDOF will have ME, HE, same thing. That's your delta D or delta E. That's your design drift. Again, depends on your hazard level and your performance objective. So let's assume it's 2.2% because that's what the example we did. So that's your theta D, but there's another concept here is instead of yielding of the rebar, like in the previous case, it's the deflection of the wall, kind of yielding of the wall at some point during the performance profile. So your wall is yielding, so theta YW, and corresponding displacement is delta Y of wall. Similar to the previous one, so instead of theta YF, you have theta YW, which is your deflection or yield deflection of the wall. Again, when you convert it into SDOF, you'll have a secant stiffness, and all that remains the same. But to get to this point, there are some additional steps that we need to, additional steps and additional equations that we need to satisfy. Now, who can tell me what a plastic hinge is? I think you're on the right track, but can you be louder?
When the movement reaches the plastic movement, mechanism develops and plastic hinges start to form.
Okay, what does a plastic hinge do? Can it carry moment? I think Mohit had a definition yesterday. Can you say what plastic?
Sectional property of a component.
Mhm.
At that particular point, the movement switches to plastic movement.
Plastic moment. And why it is important?
Rotates, that will allow rotates.
They'll allow rotation, but not. Is there a shear transfer there? So it'll allow rotation, but no shear transfer. Why it is important? Why is plastic hinge mechanism important?
It allows structure to dissipate energy.
It allows structure to dissipate energy, right? So we'll get to the plastic hinge in a minute because it's a very important concept because the wall developed some plastic hinge at the base and we need to calculate the plastic hinge length at some point. For reinforced concrete, it's easy, but for timber, I'll show you an example on Friday. It's still an assumption and there's no research that's backing this up. So in terms of design procedure, using DDBD for dual frame structures, you have to calculate the yield curvature of the wall, which is phi sub wide W. Again, 2 times the strain in the steel over the length, the horizontal length of the wall. And then you have delta I. Remember your delta I function? So your delta I is divided into 2 now. You have delta IY, which is given by this equation, if your height of the floor is above the inflection point, equal or above, and if your height of the floor is below the inflection point, that's your equation. So I'll give you a couple of minutes to note it down, and then we can move forward. Can I move forward now? All good? No, so your theta y frame. We know this equation from previously. We know these equations from previously. Then you also have your delta I as this equation here. You calculate your delta I y first, and then you plug it in here to get delta I function. Theta D is your design drift, height of inflection point, HI is the story height, height of the story from the base of the structure. Delta IY is from the previous equation here. Questions so far? And these look familiar for your S-stop system? Let me know when to move forward. Right, next up you have frame ductility. You have 2 different ductilities to deal with. You have the frame ductility and you have the wall ductility. The frame ductility is given by this equation over here. And your total overall ductility is a function of both these ductilities. In wall ductility, so it's a stiff reinforced concrete wall, right? The way it can behave in a ductile fashion is by developing plastic hinge. And the plastic hinge is generally developed somewhere along the length of the wall, towards the base. So the plastic, so maybe this entire zone is having plastic hinge development. And as the building rocks back and forth, then localized compression happens and localized damages happen that can create that plastic hinge or exacerbate the formation of the plastic hinge. For reinforced concrete, this is very well established, the plastic hinge length. For other materials, it's not very well established, and it's still a matter of assumption. But since we're dealing with reinforced concrete, the plastic hinge length is based on your yield strength of your steel, diameter of the rebar, and the height of inflection. Or it's based on this another formula. So you have frame ductility, you have the wall ductility. The wall ductility includes plastic hinge length. And the plastic hinge length is generally empirically derived, and different researchers have proposed different values, but more or less they converge at some point or the other. And all these parameters are already known or calculated previously from here. Make sense so far? So we have the wall ductility, we have the frame ductility. Now we have to combine the two to get the system ductility, right? So, first step would be to combine the two to come up with ductility of the S-stop system. So you have the wall ductility, the frame ductility, you have the moment of the wall, the overturning moment of the frame, moment of the wall, overturning moment of the frame itself. Now the next step is a little bit counterintuitive. I'll try to go slow, but please let me know if you're not following. You use this mu S-stop over here to get a time period semblance or a trial approximate value of the time period. Generally, we get time period from where? Displacement spectra, right? For the S-stop system. But here we'll do that, but to calculate our xi, or equivalent viscous damping, we need some of the parameters. So we'll use a trial time period first, and then we'll come up to the displacement spectra to calculate the actual time period for the S-stop. So plug in this equation into here, pretty easy. These are constants. What is n? Number of stories. Now, you calculate a xi of wall and a xi of frame. Your equivalent viscous damping of wall, equivalent viscous damping of frame. We needed a time period here. That's why we had to do the trial time period that we derived. That we derived in the previous step. So trial time period, plug in into these two, you get a xi of wall, xi of frame. Thank you. Yep, xi of. So we know what mu W is. We know TE trial, rest of them are number. There's one factor here which is called R. R is the post-yield stiffness ratio. What does that mean? So So ratio of stiffnesses after yielding and before yielding. So the ratio of a structure's stiffness after it has yielded past its elastic limit compared to its initial stiffness, right? So again, it's a measure of the stiffness, of how much residual stiffness is there in the structure once it starts to deform or one plasticity sets in into the structures. And it's expressed as a percentage of initial stiffness. So as MTech students who has already gone through engineering or in the final year of engineering, what do you think this ratio should be in the vicinity of? What could be an approximate number? What is stiffness after yielding divided by your initial stiffness? Should your initial stiffness be higher or lower? Higher. Your post-yielding stiffness would be lower, right? What's a good ratio? 20%, 30%, 40%?
Stiffness degraded.
Should be lower.
How much does the stiffness degrade?
7 codes.
Probably. Again, depends on the structural system, but you don't want it to degrade too much. Right? You want it to have some parity. It cannot be same, but you don't want it to degrade too much as well. So now you have equivalent viscous stamping of the wall, equivalent viscous stamping of the frame. You put them together with our favorite equation here. Again, moment of the wall, overturning moment of the frame, moment of the wall, overturning moment of the frame, xi wall, xi frame, that's your equivalent single degree of freedom system, viscous stamping. Now you can go to the displacement spectra and pick up a time period. Questions? Next step, this is a displacement spectra for 0.36 G level Indian seismic code. Take, let's say your delta D is 0.35 meter. You go to the equivalent viscous stamping and you pick up your time period. Once you know your time period, you can calculate your KE and then you can calculate your VB. So what extra steps are there between just a frame structure and a dual frame structure?
We have to calculate everything separately for frame and wall, then we have to find equivalent values.
Yes. So you have to calculate a lot of things differently or separately for frame and wall and then combine it together for the system itself. Your shape function is different. Shape function is now governed by the wall's yielding. The rest of the concepts are pretty much the same. So once you get the time period, calculate KE. There's a square missing here, so maybe please add that. Should be TE square. VB equals KE times delta D, and the distribution of forces for n less than 10 or equal to 10 is divided as mi delta I, the function of ratio of mi delta I and sum of mi delta I. But if n is more than 10, then you take 90% of VB, divide it into all the floors, and then add the 10% at the end to the roof to account for higher mode effects. Tomorrow, Professor Datta will teach you more about plastic hinges and pushover analysis, which is kind of a requirement for direct or any performance-based design. And you do pushover analysis. You can do it by hand, but that's a lot convoluted. We generally use some kind of a software, but he'll teach you the concepts of pushover analysis, and that's one of the techniques to do performance assessment or performance check for your performance-based design. Have you heard the term pushover analysis before? Yes? No? Yes? Can somebody tell me what it is? What do you push? Dr. Datta will teach you tomorrow. Any questions? Okay. So no questions. So if I give you a problem, can you solve it? How would you find out the point of inflection? Okay, let's go through an example and then we can maybe do a problem later independently or something. You need a minute or two to fire up your computers, or all good? Okay, note down the problem statement here. So you have to find lateral design forces for a 10-story building comprising of a dual system, right? It is to be designed for 2.5% drift. Take Fy, which is your steel yield strength, or the strength of the rebar as 500 megapascal. Diameter of the longitudinal rebar is 20 millimeters. Interstory height is 3.4 meters, and the ground story height as 4.4 meters. So what does that tell you? Your critical story height is 4.4 meters, or your ground story is your critical story. Floor mass is roughly 10,000 kilograms in each floor, while roof mass is 6,000 kilograms. Assume frame takes 35% of the base shear, and the rest of the 65% goes into the shear wall. And this is pretty unique to concrete, right? If you are using a spine system, then it's 100% to the spine and then 0% to the frame. Length of the wall is 5 meters. Length means horizontal length, not the height. Horizontal length of the shear wall. Depth of the beam is 0.6 meters or 600 millimeters. Post-yield stiffness ratio is assumed as 0.1. What does that mean? Only have a 90% loss or a 10% loss? 10% loss in your stiffness after yielding. And that's very typical, 10 to 0.1 to 0.75, 0.1 to 0.25 is what generally seen. Use a EC8 Eurocode 8 spectrum for soil type B at 0.4 G seismicity level, and I will provide you with the displacement spectrum. You have access to eTabs or StatPro, something like that here? StatPro? Which one is easier, eTabs or StatPro? What about SAP? Do you have SAP program here? Any finite element software, ANSYS or Abacus? If you want to go into like higher, like go deeper into the subject, there is a program called OpenSeas. It's free. There are a lot of YouTube tutorials on OpenSeas also. And there's a wiki page, WikiPy or something. It's a Wikipedia for OpenSeas. That's a very programming-based modeling software, but if you want to learn it, it'll be really helpful in your careers. If you really want to go into research. Okay, so far so good? So from this, what information can we sift out, right? Your Fy is 500 megapascal. The diameter of the longitudinal rebar is 20 millimeters. The grade of the rebar is with your Fy. Interstory height is 3.4 meters. Your ground story height is 4.4 meters, and that's also your HSC, right? Your floor mass is 10,000 kilos. Roof mass is 6,000 kilos. Length of the wall is 5 meters. Length of the beam is 5 meters. And depth of the beam is 600 millimeters. Okay. Young's modulus for steel, 200,000 megapascals. So that means your yield strain for steel is 500 divided by 200,000, which is right here, 0.0025. Following so far? I'll give you a minute to catch up. So far so good, following? Our design drift, theta d, is 0.025, right? That's what we are designing for. What are some of the assumptions? One of the assumptions that given in our problem statement is that the frame takes 35% of the base shear, so the rest of it goes into the wall system. Our R, which is post-yield stiffness ratio, is 0.1. And our site is based on EC8 and so on. Should we move forward? Everybody following? So first step, before we do anything, we have to find out what is our inflection point, okay? So we will do a little bit of math for that. We'll start with 0 and go the other way. So first story, second story, all the way to 10th story, right? These are our masses that are given to us, 10,000 kilograms and 6,000 kilograms. This is our height, 4.4, and then this would be add 3.4 to every story. You'll reach 35 meters total height. Following so far? Just populating your mass and heights, right? The table. So once you find mass and height, just take the product of the two and add a summation at the end. Following so far? Okay. Did you all get this number so far?
Yes.
Then we have to find a few things that we'll get to, but for that, you need the ratio of the product of the ith, mass and height to the sum. So 0.115 is, if you look up here, is MIHI divided by the sum of MIHI of all flows. Okay, so from now on, we'll talk in relative terms, relative between the stories. So VTI is shear at the ith, relative shear at the ith story, and which is essentially the same thing right here. Then for the next story, what you do is you add this plus this, because it's relative, right? And the check is, at the end, it has to be, so got to calculate VTI. And then please note down these three equations, which is the overturning moment at the ith story, right, for the frame. It's given by overturning moment of the story above plus the shear times the difference in height of the story, or the height of the story itself. Difference in height from the base of the story. Does that make sense? Okay. What is this? PF?
The shear that is transferred to
Contribution of the frame, which is, and why it's 0.35, because it's given to us, that's 35% contribution is taken up by the frame, right? And because it's relative, so we are dealing with ratios, so 35 is, it's a relative base shear. So base shear in the wall, or the shear in the wall, then is the shear on the story minus 0.35, which is your relative shear of the frame. So right here, if you see, it's H33 minus J33. H33 VTI minus VF. And VF would be generally given to you, or it's an assumption you'll take 20%, 30%, or so on. So this is the frame contribution. Now we went to the wall contribution. This is our total relative shear. And this is the moment in the wall, which is given by. Following so far? Getting a little bit complicated. So when you are working on, when you're populating M sub OTI or V or MW, then it's better to start from where? Because you have I plus 1, right? So it's better to start from the base. So that's the formula. And then you can go up. Your relative moment at the top of the building should be, your overturning moment at the top of the building should be. What's the overturning moment at the roof? If you have overturning moment at the roof, you're in deep issue. Your maximum overturning moment should be at the
minus
I'll provide you with a spreadsheet for you to use later on. But did somebody try populating MOTI and VWI and MW? You're trying to figure it out? Okay. Did you populate MOTI? And it's working? MW is quite similar to that, right? Again, you start from the base. You have the difference in height. you have the shear of the next story, which is this story, multiplied by the difference in height, plus the moment of that story as well.
MW को MOTI
So, okay, another trick. Moment at the top of the building is 0. So just populate 0, right? Now work your way backwards. So the next one, MOTI, is VTI So VTI at the roof, so I plus 1 is 10, because you're working with, your I is 9, right? You're working with I plus 1 is 10. So the difference in height is 35 minus 31.6, which is captured here. VTI plus 1 is right here, and MOTI plus 1 is essentially 0, because MOT at 10 is 0. So now go to the next one. It'll So if you go to the next one, which is your I is, now your I is 8. The difference in height is the height of 9 minus 8, captured right here. Your VT I plus 1, so which is VT of 9 is right here. And MOT of I plus 1, which is VT of 9 is right here. And that's what's helping you populate the 8th row. Does that make sense? If you want help, I can come and help on your spreadsheets. हो गया? साथ वालों से पूछ लो. हो गया? What about the front row there? All good? Or struggling? Did you get VTI? Okay. What about MOTI? Got it?
The same.
VF, you know, VWI from here, pretty easy. MW, got it?
Yes. That. इसका मुझे समझ नहीं आया समझ नहीं आया इसका वो पता है आज ही
Front row here, got it? So इससे क्या पता चला? What did we find out? Done? But what did we find out? So we were doing this exercise to find the point of, or height of, inflection. So, somewhere between this. You can do it mathematically, but you can then also plot. What you can plot is wall moment, MW over height. So, MW over height of the wall, or height of the building. And from there, you can figure out where the point of height of inflection is. What do you think, where it is? So it's somewhere between 20 and 25. So wall moment MW, which is your last column in your table, as your x-axis. Height, which is from 0 to 35, as your y-axis. 21.4? Good enough.
अरे नहीं सर का भी सही आ रहा है कौन सा नहीं सही आ ये करेगी ना तो हालती है सर क्योंकि वो तो सब नेगेटिव में है ना सही कर रहा है
So your point of inflection is somewhere between 20 and 25. A colleague of yours says 21.4. Mine was close as well, 21.6. Pick one and use one, doesn't matter.
तीसरे वाले पे जाओ
Also on that table that you created, make sure you sum MOTI and MW because we are going to use it later on in our equations.
डेटा सेलेक्ट होता है ना
Everybody got to the graph?
मेरा तो 21.1 अलजेब्रिक से नहीं लगा ऐसा है सही बात है राइट तो मेरे को ऐसे करेंगे अच्छा अच्छा है चलो ग्राफ सही कर रहा है
Following so far? ग्राफ बन गया? किसी का नहीं बना?
अरे हाँ पता है पर एडिट कर सकते हैं
Point of inflection, 21.4.
1.4
Okay, 21.4. So let's change this here.
21.4 पे ना 0.0
Good. Now what? घर जाना है? Point of inflection मिल गया? HINF. Now SDOF system बनाएंगे?
सिस्टम
Okay. Similar table, you can add to that columns if you want, or you can make another table like this. Previous to, similar to the previous problem that we did in the morning, right? MI, HI, but now delta IY. Delta IY कहाँ से आएगा? यहाँ से. And delta I कहाँ से आएगा? Formula that was in the PowerPoint, right?
थीटा डी
So MI, HI, delta IY from this equation. So your HI, when it's greater than or equal to height of inflection, which is 21.4, right? 21.4 is story 6. So story 6 and above, you'll use this equation for delta IY. Story 5 and below, you'll use this equation, the one in the bottom for delta IY. 5YW is 2 times strain in the steel over length of the wall. And what else is needed? You have HI, that's it, right? So you calculate delta Y. Can I trust you to plug that formula? Okay.
हाईलाइट कर देते हैं दूसरे कलर से नीचे रह सकती है
Everybody populated, delta IY? Make sure you consider two different formulas above and below the point of inflection, respectively.
क्या स्क्वायर हो ये स्क्वायर होगा ये क्यूब ये वापस से कॉपी होगा
about the story or before the
This one, first one. It's greater than equal to.
ये फॉर्मूला बता दो DIY का ये सामने भी लिख रखा है ना
So once you find delta IY, delta I is delta IY plus, and then in brackets, theta D, which is 2 point something, minus phi y w, phi y of wall, which is given here, height of inflection, which is 21.4, divided by 2, multiplied by the story height, hi. And it's same for all the stories. The formula is the same for all the stories. Following so far? Delta IY and delta I. The main work is finding delta I. Once you find delta I, everything should be simple from there. Following so far? How many of you, raise your hands, how many of you have found delta IY? Okay. How many of you have moved on to delta I? If you've already found out delta I, then you can move on to the next step, which is the product of mi delta I square, and mi delta I hi.
यहाँ पे लिखना था, लिखा पढ़ने के यहाँ पे आता लिखो इक्वल्स टू 5/w into
Okay, who's gonna tell me me? What's your equivalent mass? What's our equivalent mass? Remember these formulas over here?
not matching with yours. Both the highlighted points.
They're not matching, right?
Yeah. Rest all are correct.
How much is it off by?
Delta I is DIY is 0.17033 for the first one, 10 story.
This one?
Yeah.
0.17?
033. आपका भी
some difference है sir.
Some difference है, but 0.17 है क्या पहले वाले का?
तभी तुम्हारा पिछला बन गया.
Let's see.
Same है.
क्या हो गया? मैच हो गया?
हाँ सर.
मेरी वैल्यूज ही गलत है तो कैसे मैच होगा?
सर हमारा तो हो रहा है.
हमारा गलत मैच हो रहा है. नहीं सही हो गया फिर वैल्यू हो गया.
देखते हैं
वैसे मत आओ.
आप तो चेक करते हैं ना अपन ने कुछ गलत किया होगा अपन तो चेक कर लेते हैं.
और किसी का मैच हो रहा है?
इन्हीं का गलत.
इन्हीं का नहीं.
0.179 तो गड़बड़ है, बट इनका भी थोड़ा सा ऑफ आ रहा है.
0.799.
चलो अगर मैच हो गया तो बताओ एमई, एचई और डेल्टा ई क्या आ रहा है?
ME 73294.
7.3.
94 ME.
डेल्टा ई
533.
0.5.
24.32.
Okay. And this is similar to what we did previously in the morning with the single system, right? All the formulas. So delta D is 0.534, ME is 73294, HE 24.32 meters. Theta YF is from this formula given by Priestley. It's 0.5 times the strain times the length of the beam in that direction over the height of the beam in that direction, or the depth of the beam in that direction. आपका फॉर्मूला ठीक हुआ? नहीं हुआ?
Issue I'll check.
LB is 5 meters, length of the beam, height of the beam is 600 millimeters or 0.6 meters.
सबमिशन
तो इसी समझ में आ गया मैंने लिखा तो सही इसमें टाइपो इधर पे.
Okay. Now we will have to calculate frame ductility. And frame ductility is for every story. So we need MI, HI, delta I, which we can copy from above, and then we can calculate mu F. So mu Fi is given by this equation here, which we also did in our right here, our frame ductility equation. So add that into your Excel spreadsheet. Your frame ductility equation will give you the frame ductility for each story, and then you do an average. You do a sum and then an average, which is roughly equals to 2.2, but we can see what you get. This is delta I minus 1 divided by the difference in height of the same two stories and the whole thing multiplied by 1 over theta YF.
into LB बता length of the beam है ना divided by 2.4
cutting L05 we can
Everybody following till frame ductility? Mu F?
Yes, sir.
So mu F varies with different story height. We generally take the average when we're calculating the other things that we need to calculate.
कॉलम किस किस की बनाई है सामने
Let me know when everyone has reached this position, we'll move on. So for mu F, just populate the difference in delta I plus delta I minus 1, delta I minus 1, divide by the difference in height, which is HI minus 1, right? And then that thing then is multiplied by 1 over theta YF, and theta YF, as you calculated before, is 0.5 times EY, which is 0.0025, LB, which is 5 meters, divided by HB, which is 600 millimeters, or 0.6 meters. And you'll get theta YF of 0.0104 radian. कंडक्टिविटी आ गया Got it? Now have fun with plastic hinge length. So you have two equations for plastic hinge length given here. You have to use the minimum of the two. One includes your some steel properties, the other one is more geometric in nature. So the minimum of the two should be used as a plastic hinge length. Once you calculate the plastic hinge length, which is given by those two equations, you have to take the minimum of the two. So Fy is 500 megapascals, dB is up there, diameter 20 millimeters. And then plus 0.054 times the height of inflection. The other equation is plastic hinge is 0.2 times length of the wall plus 0.03 times the height of inflection.
बता दो into FY into DB the data being
डॉलर लगा दीजिए
Did you get this? For your plastic hinge length, 1.3738.
या
1.642 is for the other one. So we'll use the minimum of the two, which is 1.376 for a plastic hinge length. And then once you find out the plastic hinge length, use this formula here to calculate the ductility of the wall. LP, you're finding out from this equation, 1.376. 5IW is somewhere here. 0.001 radian. Theta D is our design drift. 5IW again, height of inflection divided by 2. Our 5IW we calculated out here, which is 0.001. Following so far? Let me know when you find out. Yes.
FY will be 500 and DB will be
DB will be
20.
20 millimeters. It's the diameter of the rebar.
B2 और divided by
So 0.002 C8 times C9, which is 500 times 20, divided by 1000. C9 is divided by 1000 because of millimeters. Plus 0.054 times I45, which is height of inflection.
11.39
Getting the same answer? So 1.376, and then calculate mu of wall, which is given by this equation over here. Let me know what number did you get for mu of wall. 11.395. So we can probably do it as 11.4, rounding it up. So we have mu of wall, we have mu of frame. We'll take the average, which is 2.2. Mu of wall, mu of frame. You have to find mu S-DOF, which is, we need the overturning moment of the wall, overturning moment of the frame, which will be given by your first table. MW and MTI. That's why I wanted you to sum those at that point in time. So, your MS stop, mu S stop is, if you look, you have your L40, which is L40 is 11.49, which is your overturning moment of the wall, and then I40 here, which is your overturning moment of the frame, times your 2 mu's, which is a 2.2 for wall, for frame, and 11.4 for wall. Plug in this equation, you should have roughly 5.2. Everybody getting that number, roughly? So once you have mu S stop, you have to find a trial time period, which is a story height 10 divided by 6 times the under root of mu S stop, right?
That's right.
Which is 3.8. Now, have fun with these formulas. So xi w and xi f is what is needed. You have mu w, you have TE trial, which is 3.8 seconds. Please make sure to take care of the units. And then what you need is R. What is our R?
0.1.
0.1, our post-yield stiffness ratio. 0.1. So once you have those, you might have these numbers. If you have little skills with Excel, you can probably build a template where you can input number of stories at front and that'll do a macro workbook, and then everything can be populated easily. Who has EW or XIW already calculated?
13.75.
Yep. And XIF? So here's the formula if you're looking to how to input it, is 95 over 1.3 times pi. So that's in one parenthesis or one bracket, and then 1 minus mu times, or raised to the power negative of 0.5 minus 0.1 times C22, which is essentially our R, 0.1, times C105, which is our mu W, times, again, bracket 1 plus bracket again, T trial plus 0.85 raised to the power minus 4. Whenever in doubt, use brackets in Excel. Got it? Both xi w, xi f converging?
9.6.
Okay, now xi s dof, which is xi of w, xi of frame, moment of wall, moment of frame. Only get 10.5%. So again, xi of wall times xi of moment of wall times xi of frame times moment of frame. These are the moments we calculated in the first table when we were trying to calculate the point of inflection. So right here, 23 and 11, and then the same 23 and 11 in the denominator, the sum of that. It's 10.5. Anybody not getting 10.5?
10.9 now. Same page. 10.9.
Okay. So now you have damping, the effective damping of the single degree of freedom system, which is roughly 10.5, give or take. You have your delta D somewhere. Somewhere you have delta D, 0.534. We'll go to our displacement spectra or our xi 10.5. Our displacement 0.534, right? And we pick up our time period as 4.5 seconds. So our time period, equivalent time period is 4.5 seconds. So our Ke is 4 pi square me over T square. This is our equivalent stiffness for our S-DOF system. Ke times delta D is our VB. N is less than 10. So our Fi is VB times Mi delta I over summation of Mi delta I. And you don't need these here, I just put it. But that's how you will distribute the forces among the story height. Does that make sense? Is this part clear to everybody? The last one? You find VB from your KE. You find KE from your TE. You find TE from displacement spectra. And once you find your VB, just distribute it along the story height to get the story shears. Convoluted process? Done? You have the same numbers over there? Anybody still working on it? So a lot of going back and forth and referencing different formulas and different previously calculated values. So you just have to keep track of what the steps are and how your ultimate goal is finding SDOF properties. And how do you find it is will dictate your steps. Any questions?